Okay, so people can see my slides, right?
Yes.
Okay, sounds great. Let me get started then. So for today's meeting, I'm going to talk about some recent progress in explaining GNNs. Specifically, I'm going to mention two papers, one from NeurIPS 2021, another will appear in NeurIPS 2022. I don't know if you remember around the same time, November last year, I gave a talk in one of our paper reading groups about explaining GNNs. So today can be like a second round of that. For those of you who were not here yet last year, I will also do like a quick recap of this topic. But for myself, I have been working on this for the past 1 year. So I guess other than these two papers I'm going to talk about, if you have any general questions about this research topic, just feel free to interrupt me. I will try my best to make things clear to you and answer your questions. And then I will start by doing that introduction. You can think of it as a recap, using two slides to go over the general idea of model explanation and GNN explanation. And then if you want a more detailed slides of this general topic, you can check here. This is from my last year's presentation. And then once this part is clear, today we will focus on these two works, one called Towards Multi-Grand Explainability for GNNs, one called Task Agnostic Graph Explanation. So both of them are not very deep, although they use a little bit like fancy notations and define some new concepts. But as long as you follow me when I'm talking about this general idea, these two works should be like pretty easy for you to understand. Okay, let's get started then. So to start, I want to first talk about model explanation in general. Basically, when we say that we want to explain the model, it can mean like many different things. But the most generally, people usually mean we try to identify some important features where for a particular prediction made by a black box model. So this sentence is concise. There are like several things we want to like pay attention to. First of all, these important features, the feature itself can refer to many different things. Like in images, the features can be pixels, and then in text, the features can be words. In graphs, it can be graph nodes and etc. So here we're just talking about it in a very general sense. Then the second thing is that we're talking about one particular prediction. Previously, people try to develop things like what they call interpretable model. For those kind of model is that by nature of the model is interpretable. So we don't do any explanation of it, we just use it, and then it will explain itself. One example is like the linear model, right? If you just look at, if you just do a simple logistic regression on tabular data, then you can look at the coefficient before each of the input attribute. Then that coefficient tells you how much contribution the feature made to the final prediction. So you don't need to look into individual predictions. But for most of the black box models, like neural network-based models, we usually need to deal with these predictions one by one because we don't know how the model works, like how those neurons are fired to get the final prediction vector, etc. There is also this line of work people try to do interpretable neural networks, but that's like a slightly different thing from what we're talking about today. And then the good thing to have a model explanation is that we can improve the model transparency. So that means when you are as a researcher or developer, when you are developing your model, you want it to be transparent. Why is that? Like probably you want to use your model for some critical decisions. And then for these critical decisions, you want to say avoid some risky conditions, or you want to try to interrupt and get manually control when your model has really low confidence, etc. So if you know how the model works, you can decide when it's risky, when it's not. You can decide when to interrupt and not, right? But if you know nothing about the model, it's just a black box. You give it input, it spit out an output. It's kind of hard to decide how to interrupt. And with this kind of low frequency, low transparency, it's also very hard for you to debug the model. Even if the model went wrong, because it's a black box, you are not sure whether it just went wrong or your model just didn't work for this particular data instance. So that's from the researcher and developer perspective. On the other hand, if you are just a user, like you know nothing about machine learning, you just want to use this cool AI technology to help you do some smart things. Or a basic example is like you go online, you want say you go shopping and then you see some recommendations made by the smart AIs saying that, okay, this product is perfect for you, you should buy it. But in this case, if I just get random stuff saying that, okay, this is good for me, I should buy it, why would I trust that, right? But if I have an explanation associated with that recommendation, things can be a bit different. Like saying that, okay, you give me something for me to consider. At the same time, you give me a reason. If I think your reason is reasonable, then I will probably consider buying this stuff. And I will also trust your prediction, saying, oh, you are not making random prediction to me. You are giving me this good reason that I think is reasonable. So in this case, not user trust, but also user engagement and user satisfaction will both be improved if we can properly explain the model. Okay, these two bullet points sort of answers what we are doing and why we're doing it. If it's still a little bit abstract, we can look at some examples. Back to 2014, people started to work on this model explanation tasks. And of course, at that time, most of the, say, the representation learning or machine learning were centered around the images. So they started analyzing CNNs on this image classification task. And then what they do is that take this black box, right? It's some kind of CNN model. If your input is an image of an elephant, then your model classifies it right as elephant. And the question you ask is that, why did my model classify it as an elephant? In this case, it's for a particular prediction, just for this image. And what you are trying to do is trying to figure out the important features. So feature in this case means pixels. So what your explanation method generate is this heat map associated with the image. We can roughly say that, okay, here maybe the elephant's head, and especially the elephant's nose, etc., saying that, okay, with this heat map, it explains which pixel is important for this prediction. So you can use that as an explanation. So later on, in 2017, there is another a seminal work using the Shapley value from cooperative game theory, where they generalize the explanation idea to all different kinds of features, from tabular data to image to text to anything. As long as you can collect these features, this NeurIPS 2017 paper formalized things as a cooperative game and solve the problem of attributing importance to features as attributing payoffs to players in the game. So by making this setup, they can solve the problem. So one example is saying that I have a black box model, doesn't need to be CNN or any neural network model, just any black box model I try to explain. Then let's just use the tabular data as example. In this case, I know the patient age, sex, and blood pressure, and I output the probability for the patient to have, say, certain disease. Then I can, through the explanation model, do this analysis saying that, okay, which feature, in this case, the input attribute contributed more to this prediction, and which feature contributed positive, which feature contributed negative. All these questions can be answered. And in the graph case, we can also be more specific about let's say this molecule graph, we're trying to explain its prediction. So basically, this is also usually used as the example when you read a gene explanation paper, because if you want to do things like, say, drug discovery, this kind of prediction can be more critical. You need to really be careful about what's going on here. So if you have this input molecule and then your GNN, which is also a black box, classifies it as mutagenic, then you probably want to say, okay, which functional group within this molecule is the reason for classifying it as mutagenic. This is something like really intuitive, right? I mean, maybe for chemists at least, they can probably don't use any machine learning model, just look at this molecule based on their experience. They can point out, okay, two functional groups working together, making it mutagenic. But in this case, we want to have an explanation method that sort of tells you maybe this highlighted NO2 functional groups were the reason for making the prediction. And also, recently, people also try to combine this different data types. For example, they converted the text into this dependency graphs. Like this sentence is still quite good natured and not a bad way to spend an hour. People do the dependency tree and use the word dependency to connect the words together, construct this graph. If you use GNN to do sentiment classification, the GNN can probably correctly tell you, okay, this sentence is a positive sentence, but then we want to have some explanation method to help us identify like which word, which phrase actually played an important role for identifying this positive prediction. In this case, it's probably this subgraph on the top right, still quite good natured. Okay, this is the general idea of model explanation and especially the last two examples, GNN explanation for what we are doing and why we are doing it. Then I'm going to talk about like at the beginning how people approached this problem. Right now we have more different approaches like in the image. So if we get back to here, I can briefly tell you in this image case, it's just using gradient-based method. In this 2017 paper, they were using cooperative game theory. So right now we have more different methods coming up. But the two works I'm going to talk about today, they have their new ideas, but they basically follow the very first work in this domain called the GNN Explainer by Rex Ying from, I think it's Europe's 2019. So in this slide, I'm going to tell you the general idea of GNN Explainer, and then please make sure you understand what's going on here, because this will save us a lot of time for understanding the other two recent works. So as the last example I just showed on the previous slides, the goal here for doing GNN explanation is that we try to identify the important subgraphs for why GNN is making this prediction. And the problem is that when we talk about subgraphs, you can imagine even you only have, say, 2 dozens of nodes, the total number of subgraphs is still very large, right? It's exponentially large in your graph size. So it's hard to talk about all the subgraphs in for making this kind of prediction. If there are just 3, we can maybe just enumerate them and check which one is better. But because there are many of them, people usually reduce the problem to find edge-induced subgraph or node-induced subgraph. Basically, they just identify important edges or nodes, and then at the very end, they get the induced graph. So just for the scalability issue. And besides scalability, another challenge is that because graph structure is discrete, right? So we saw in the image case, we can just take gradient with respect to each input pixel, then we can probably get the heat map telling you which pixel had the highest gradient when plugged into the GNN, then you are basically done. But in this case, for the graph structure, it's hard to generalize this gradient-based method. That's why we talk about considering all this node and edge-induced subgraphs. Otherwise, if it can be done using gradient, we actually don't worry about exponentially many subgraphs. We just use gradient method to help us to find out. So this is another challenge. So that's why this Gene Explainer paper try to approach the broad problem via mask learning. So what do I mean by mask learning? So basically, what they try to find is this edge-induced subgraph. What they do is that they parameterize a mask over all edges in the graph. So you can think of this as like a initialization. At the beginning, you have this input graph, and you have this GNN, which is already trained just for you to explain. What you do is that you use like a set of parameters, like 3 parameters, each one associated with one edge in the graph. Then this set of parameters will be your mask. And the purpose of your mask is to figure out which edge is important, right? You apply the mask on the edge, and then through later learning, the mask will change its values to select out some edges and mask out the others. For the selected edges, you can use them to generate this induced subgraph. So mathematically, this is saying like, I have this input graph G with nodes V and edge E. Then I will just initialize this mask M, which has the same dimension as number of edges, but are just full of 3 parameters. Then by applying this mask on the edges, what I mean is that I use this sigma means the sigmoid function, and then I multiply. This is like element-wise multiplication, and then I multiply it on this E. Then I will get the selected E, and then I can use that to select the nodes as well. Basically, for the dropped E, if it disconnects nodes, I don't need them as well. But at the end, through masking, I can get this selected subgraph G. So this is when using the mask. You can sort of think of it as like the inference step. If your mask is already a good mask, this is how you get the subgraph. The next thing is that, okay, we have the mask, but it's full like a random parameters. How can we have that good mask for us to pick out the subgraph? So Gene Explainer choose to learn this mask by maximizing the mutual information. So it is something like this. So originally your model made a prediction and gives you a prediction Y. And then this Y, we got it based on the full graph, like this original G here. Now you apply your mask on your G and you get this selected graph GS. Then you train this mask by maximizing the mutual information between these two, right? So in other words, what I'm saying here is that I have a given graph, and then I have all different possible ways of masking it out. But I want to find that particular mask such that the mask graph and my original prediction, their mutual information is maximized, right? Equivalently, this can be written as minimizing another more direct loss, the prediction loss here, right? So because GS, we got it through masking, so this is actually just minimizing over the mask M. So this prediction loss is simply the following. I'm not showing it the intermediate derivations. You can check the paper if you like, but this should be pretty straightforward to you, because what we are saying is that, okay, now I have these edges that are masked. I want to use it to make the prediction, and Y is the prediction from my original graph. So I just want to make sure this loss is small, which means this log probability is large. This is just saying I'm just trying to match the original prediction, even though my graph has this edge, all the edges masked, right? So this is what I'm saying here in this last sentence. Okay, I said a lot.
Can I ask a question here?
Yes, please.
Is there the mask? Is there any like size limit of the mask? Because otherwise, I would have the everything right being selected. Then that's matches Y, right?
Right. Yeah, this is a great question. So what people do is that not only just this paper and several following up paper is that when they define the problem, they just say, okay, this is the mask they want. And then when they do the actual training, sometimes they will add another regularization terms. They call it, say, the budget regularization, saying that
that controls how big that.
Right.
I see. Mm-hmm.
Yeah, the budget regularization, I only want to say like 10 edges or so. Sometimes they will also include another regularization, they call it entropy regularization. Because when we train this mask M, it can happen that many values are like in the middle, like 0.5, right? So that's not good. So they also add an entropy regularization to make sure they get discrete values like 0 and 1, so they can make proper selections. Yeah. Yeah, thank you for the question. So even in the original gene explanation paper, these kind of regularizations were mentioned, but like only really briefly in 2 sentences. What people found was that a proper regularization can be important for your model to achieve good explanations, but it can also be like data set dependent. So at the beginning, they'd rather to define this very general framework for all data sets. Then later on, maybe tune the regularizer or hyperparameters for different tasks. Say for the molecule case and the sentence or dependency graph, you probably want different budget for explaining them.
So, Shichang have a couple of questions. So here, just wanted to confirm, your Y is graph level task, or it could also be node level task.
So yeah, this is also a good question. In this paper, it contains 2 cases: graph prediction and node classification. So for node classification, what they do is that they first extract the computation graph. Basically, if you have 2-layer data, just extract the 2 hop neighbors.
For node classification task.
Yeah, so they also cover node classification, but just the ego. So they just extracted an ego graph, like for the node you try to classify. Yeah.
I see, because the graph level is kind of more intuitive, but for node classification, you're saying, okay, let's consider ego network and try to understand which local structure is accountable for this particular class label. Is that right?
Mm-hmm.
I see. Great. Another question related to the claim you made for the challenge part. It says that discrete graph structure prevents gradient-based methods. Then a natural extension is like we kind of relax the agent matrix, right? So of course you say orange agent matrix is kind of discrete 0, 1, but we somehow can relax, try to allow each age with a potential continuous number. So by doing this, do you think the problem can be just simply solved?
I think that's actually aligned with the intuition for Gene Explainer and this mask idea. So because like their story is like they also try to do this relaxation to make the edges like number between 0 and 1. But they choose to do that. They use this masked value to represent that we can think of it as a probability between 0 and 1. Yeah, and then you can think of it as the original adjacency matrix is discrete. This mask is a sort of like a soft adjacency matrix.
Okay.
Yeah.
Great. Thank you.
Okay, so yeah, I said a lot. Yeah, thank you for the questions. Any other questions from the audience? Because it is important that you understand this slide. Yeah, both works I'm going to talk about the builds on this slide. Okay, let's move on. Yeah, if you understand that, everything for today will be easy. Okay, so the first work, this is from NeurIPS, last year's NeurIPS 2021. So they call it towards multi-grand expandability for graph neural networks. And then I will first share some of my own opinions, like my own general comments about this paper before we look into the details. I personally think that the question this paper asks is definitely enlightening. And before reading this paper, I actually had some similar but not exactly the same ideas about how to do graphic GNN explanation. And then they are giving some try along that direction. So I think the question part, we can definitely learn something very interesting. But in terms of the method they propose, I guess it's probably not the best method. We can look into it together and see whether you agree or not. But I feel like the method they propose here is a bit of mixture of different things. Probably because when this paper was proposed, the idea of pre-training is very hot. So they actually used a lot of fancy terms, saying like pre-training and fine-tuning and etc. And attentive graph and those things to make the paper look a bit complicated. But we can see that those things are definitely not deep. We can simply talk about those things in the mask language I just introduced in the last slide. So I would say when I'm talking about this paper, we can focus more on the question, and then we can take a grain of salt when we talk about this method. So okay, so what this paper is trying to do is that they at the beginning distinguish these two things. One they call local expandability, one they call global expandability. So for the local expandability, the question they are trying to answer is that like why the GNN model made that particular prediction for that particular instance. So this is really aligned with our definition of what GNN explanation is doing, and I think most of the GNN explanation papers are addressing. But in this paper, they call this kind of problem only local expandability. So they also propose something called the global expandability. What they call global expandability is that like the class-wise knowledge GNN can leverage to make the prediction, right? So let's look at this using the molecule example here. So this is the same picture I showed you a couple of slides ago. You have this input molecule classified as mutagenic, and you try to explain it by finding out the critical functional groups. I think for local expandability, what we are saying is just for this instance, we want to find out this important functional groups. But for global expandability, it can be something different, right? For example, let's say if I have a map that can map all different patterns that might appear in a whole set of molecules. Say you can think of it as like a list of different functional groups or a combination of functional groups. If I know for that kind of map, mapping the functional groups to these properties, for example, mutagenic or not, then I actually don't need to do local explanation for each graph. I can just take a graph, look at my list, check whether it has those properties, have those functional groups. Then I can just say, okay, whether functional group NO2 maps to mutagenic, seems like so, and I have 3 of them, then I will classify it as mutagenic. Then this kind of mapping the patterns to the predictions can be the class-wise knowledge, right? So if you are doing, say, 10 class classification, for each class you have the functional group associated with it, then you are done. You don't need to have a complicated mask or anything to tell you. You just check the functional groups. The problem is that we generally don't have those. Even for the experienced chemist, they probably don't have those, right? So, or maybe the rule is not that direct, not like a lookup table. You can just look at functional group and their properties. There is some more complicated interaction going on. But definitely we can leverage this kind of knowledge, bring it together with the local expandability to make the explanation method more powerful. And that is what this paper is doing. In another way, you can argue that, well, even though I don't have this global explainability information, I just use my black box GNN to make prediction on my own molecule. Then I should have like enough information for me to identify which is important, like which functional group is important. I think that kind of argument also makes sense. We do have enough information, right? We have the information for us to look at the molecules one by one. The problem is that if this kind of explanation method can be hard to learn, or in other words, it's hard for you to find a way to actually figure out which subpart was important for a particular molecule. You have to do it like a one by one. But if you can give it some global explainability, like more general class-wise guidance, it can probably can give it some good inductive bias to make this local problem much easier. When I was thinking about this, I think it can be connected to the diffusion model idea we talked about in the past 2 weeks. Although not like exactly the same, but I personally can feel some shared intuition there. Like if you remember in the diffusion model case, when we try to do conditional generation, we also had that classifier guidance, right? We had classifier free guidance and other guidance, but we had that classifier guidance, right? In this case, incorporate this class-wise level knowledge into explanation has the same integration as include the classifier guidance into your generation, right? You can see that as long as my generative model is good, I don't need any guidance. You're already telling me to generate a cat. I don't need a separate information saying that, okay, the image you need to generate belongs to the class cat, because I already see the word cat in my prompt. But somehow when you include both the cat prompt and the classifier guidance telling you the label is cat, you can generate better cat images. In this case, I guess this similar thing, telling you this molecule is in which class can give you some better guidance for you to identify the useful functional groups. Okay, any questions about basically like the general question this paper tries to answer? I think this is the most valuable thing of this paper. Okay, then let's move on to what this paper is doing exactly. So they call their method refine. And then in this refine method, they have 2 stages. One they call pre-training, one they call fine-tuning, according to these 2 pictures below. And then we will break it down, look at what's happening for these 2 modules. But before that, let me clear some notations they used in their paper. First of all, given a graph G and a GNF, try to explain, and then you also need to know, this is instance-wise, you're just looking at a single graph, and then you need to know like what F predicted about G, right? So it can be the class C, saying that F classified G as class C. And then like Wei's question before, in this case, they are considering this budget rule, which will be useful in their second fine-tune stage. But they have this budget rule. And then they define something called the silency map. Okay, silency map. It's actually just the mask. What we call it mask, but they call it a silency map. What they are saying is that this mask is this M. The dimension is like n by n, like the number of nodes you have. But it comes from this function T. So here is a little bit different from the GN explainer idea I introduced. Although it is also a mask, but the mask is not like a set of free parameters for you to update, right? In the GN explainer case, M will just be this matrix, this tensor with n by n free parameters. But in their case, it's not. In their case, this M will come from another function T, which takes in the graph G, the GNF and the predicted class C, and outputs the M. We will check that in next slide when we talk about pre-training. And then once you have this M, they call it, you can get the mask graph by applying this mask on the edges. In this case, they call it a tentative graph. Yeah, but the notation is GATT, but this is just applying mask on it. And then besides this, they distinguish a tentative graph from another concept called explanatory subgraph, GEXP. But what this is saying is that, okay, I have this tentative graph, but I will do some further sampling and thresholding of it again, and get this another mask, the matrix S. This S is actually also you can also think of it as a mask, and we got that by plugging into the attentive graph into this function H. What H does is that sort of like a sampling and thresholding, because you see here we have this extra budget parameter. So in the attentive graph step, F is still a matrix full of say probability values, like values between 0 and 1. But by plugging it into H, according to that probability, and or doing the top edges by cutting the top edges off based on your budget. So at the end, when you get the output from H, you get this another mask matrix S, but with only values 0 and 1. So this is like a hard mask, and also the number of left edges should be small. And then, so when you apply this S on the original adjacency matrix, you get this explanatory subgraph. Because S is discrete and small, it only corresponds to a very small portion of your original graph. Okay, so they distinguish these two things because they're going to use the GATT for what they call the pre-training stage, and use the GEXP for what they call the fine-tuning stage. So let's look at what's happening for these two stages. So for pre-training, the input is like a graph, and then they will do class-wise attribution module. What do they mean by that is that they will have different T functions, right? Imagine you have in total big C number of classes, and then they will have one T associated for each class. So because our mask comes from this function T, right? And then in this case, you can see that if you know what is the class, this small c, if you know this small c, you know what the class of, what is the class label of your input graph, you will pick that particular T. So basically you have different T's for you to pick. Each one will, even though maybe the G and F are the same, it will give you different M. So in this way, they think of it as different T stores different class-wise information. And in particular, how did this T gives you the M for masking, right? What they do is that they get the node representations, plug in it into MLPs, and do reparameterization. Okay, this is I'm going to use some formulas to make things clear about what's happening here. So what I'm showing here all happened inside this T, okay? So you have the input G and F, right? This F here, and then you have this input graph G. What you will do is that you first plug in the G and the node features into this GN to get your node level representations Z. So the dimension of this Z will be the number of nodes by the feature dimension. And then this G also for each of this T, it also contains this MLP module, which will take two node level representations and output a scalar value. This is, you can think of it as link prediction. This is saying that once I have the node representation of I and J, I can concatenate them together, and using this MLP to predict what should be the probability value of the link between I and J, right? You can imagine this alpha ij, which they call the attentative, will come into your mask, right? Because your mask is just doing pairwise link probability, and here is link prediction module for you. What they do is that, okay, they add one more step on it. They do this reparameterization. Basically, they sample this epsilon from the uniform distribution, and they do this transformation here by converting this uniform transformation, uniform random variable into a random variable with range in R, plug it, add it on Aij, renormalize, and go through sigmoid. Okay, this is just some transformation, but what they are preserving is actually just the information from alpha ij. All others are just for derivation and modeling purpose, because they try to formalize it as a probabilistic model. And then finally, once they have this probability for each mij, right? You already have it here. Then you can just use the same loss function we mentioned in GNN explainer, right? So I mentioned that it's derived from maximizing mutual information, but what it does is just take this whole graph prediction. Here, this J is the original J, and here this is log of the like the attentative graph prediction. This is pretty much like the cross entropy loss, but with outside the original prediction, inside log the tentative graph prediction, just to minimize this, right? Here they have 3 expectations, but this is nothing complicated. This is just saying we should average over different classes, average over different epsilon we sampled, average over different graphs in the data set, right? The core idea is still doing this like a mutual information loss.
So John, for this slide, can you explain this MIJ and what's the role of the epsilon?
Explain the role of the epsilon?
Yeah, and also MIJ.
MIJ. So, okay, so basically all this, the first 2 lines here are meant to explain what's happening inside the function T. And then you want the function T to output an M for you, right? This M is the matrix M, and each of its entry is here. That's
so what's the semantic meaning of this MIJ?
This M is just the matrix we want to get. Like if we go back to the GN, like in this case, we have this mask, right?
It's just a mask.
It's a mask. And then in this case, it is simple because this mask is just a bunch of parameters we try to optimize. Okay, but in this case, the mask is no longer a bunch of parameters. The mask comes from some T. This T is this it's a function with the GNN and with MLP in it. Right.
Then the mask, the MIJ essentially is going to be a value between 0 and 1, right? It's like soft mask.
Yes.
Okay, then inside that sigmoid function, sigmoid is trying to turn something to 0 and 1. So what's the role of this epsilon? Okay,
so this is because when they call it a reparameterization, right? So when they set up this model, they set up everything using a probabilistic model, and then they're saying that I have some random variable, but my prediction, this alpha ij here, shouldn't be random. The randomness should come from a separate random variable epsilon. So in that case, although what they are trying to do here is just to apply the sigmoid on this alpha ij, right? So you can imagine if you have an output from MLP, you just apply sigmoid on it, you can get values between 0 and 1. But in their case, they try to separate the randomness and their prediction. So they are doing this transformation of the Aij and then plug it into the sigmoid.
I see. So it's kind of the version of autoencoder framework. They wanted to inject some randomness, and then they apply this reparameterization trick. So then they can separate the parameter part and the randomness part.
Right. Yeah, it's just in the VE case, it's a normal distribution. In this case, it's just uniform. Yeah. And then, yeah, lastly is loss. It's a part of the loss functions, because in their pre-training stage, they actually used like two loss functions. One, they just call this mutual information loss. The other is the contrastive loss. We will look at it in next slides. Any other questions about this slide? Okay, let's look at the contrastive loss. So for the contrastive loss, I think many of you are also very familiar with it. The basic idea is that similarity maximization or minimization. So basically for the things that you believe should be similar to each other, you compute their similarity score and try to maximize it. For those things shouldn't be similar to each other, say from different classes, you minimize their similarity. So in this paper, they just take a very standard contrastive approach and add it on top of the mutual information loss, where we usually use for explanation. So basically it's saying like, okay, I can have two attentive graphs, right? So these are just the masked graphs, but they made from two different classes, because during this stage, you are looking at all different graphs in your data set. You try to collect the global information among them. So whenever I have two graphs and I get their attentive graph, I can compute their similarity by just doing the dot product between their representation, right? So I can encode these two graphs with GNN to get their H and dot product H. Then I can do some transformation using this the soft plus function. If this is not familiar to you, what the soft plus function is doing is something showing on the right. It's like very similar to ReLU, but it is continuous. So it's like a continuous approximation of the ReLU function. So what they are doing is that they take this similarity between the two graphs. This one goes to here, right? And then plug it into this soft plus function, and then times it by this indicator. So this indicator is just telling you when they are from the same class, right? In this case, it's loss, so minimize it. So when they are in the same class, minimize it. When they are in different class, maximize it, right? So if this loss is minimized, then the similarity will be maximized. So this is what they call the contrastive loss. Okay, any questions about it? Okay, yeah, if no questions, this is just what they are doing by what they call the pre-training stage. So for the pre-training stage, it's different from the GN explainer case, because they need to check all the graphs in the data set and then try to extract what they call the global level information among them. And then later on, they feel like this is not good enough if they just do the pre-training. They need to do something more similar to the GN explainer case, like look at each individual graph. So they have this separate fine-tune stage. This is also where this GEXP will comes into play, right? So we talk about it. Originally, there was GATT, which is like a softly masked graph. But now in the fine-tune case, they will generate this GEXP, which is a hard masked graph. So what they are saying here is that, okay, I will use this H function to help me to get this S for the masking in the fine-tune stage. But what this function does, H function does, is simply a selection module. In this case, right, because we have the budget row, we can probably just take the top row edges, and then And then this will turn the GATT to the GEXP. And then what you are doing is that you also want to train your T a little bit using the same loss function, but just the graph here is replaced with GEXP rather than GATT in the pre-training stage. We can compare it with the pre-training stage. These two loss functions are exactly the same, right? Just except that this graph is replaced. So in the fine-tune stage, basically you drop the contrastive loss, you use the same loss to further train the model a little bit with this extra selection. And then by
实际上就是 try to double confirm for the fine tuning stage, we assume we do have the ground truth subgraph.
no, we don't.
So then how do we have that explanatory subgraph?
So this explain. So we have this attentive graph, right?
Right.
And
In
then
the pre-training stage, right?
right in the
Okay.
fine-tune stage, we just sample from it. The paper actually proposed two different ways to do it. One is sample from it. One is just to take the top row values of it. So let's say you just have three edges, 0.1 to 3. And then if I just take the top one, I will just keep the edge with 0.3 value probability and drop the others. Then that will give me the explanatory graph.
Okay, probably I kind of, because it's fine tuning, right? So I just try to understand what kind of guidance are provided in the fine tuning stage. Because of course, this is like different setting. We're talking about explainability, but it's just to think about other general deep learning model in the fine tuning stage. We do have additional labels, but pre-training stage we don't have like task specific labels, but just a self-supervised tasks. But here, yeah, just try to understand better about what does this fine tuning mean here. If it's just to select the top ones, then why it is called fine tuning?
Yeah, so I think this is a great point. This is also where I don't quite agree with their naming style of different modules. So like you just mentioned, usually if we have a pre-trained fine-tune framework, the pre-training will probably do it with say contrastive loss without any labels, right? And in the fine-tuning, we just for whatever task we have, we just use that label to do fine-tuning. In this case, it's different. For both stages, they don't have the labels. For both cases, they only have this mutual information loss. It's just that for the pre-training stage, they have both the mutual information loss and the contrastive loss. For fine-tuning case, they only have the mutual information loss.
Okay, so at least, yeah, I know what they are doing. Thanks for the explanation.
Okay, yeah. Any other questions? Okay, so we can look at some of the experiment results they show in the paper. Because you see that up to this point, the whole intuition is also very similar with the gene explainer, right? Try to use mutual information to quantify how important the subgraph is and a learning mask to select it out. The difference is that they have two stages. The pre-training stage for global information and the fine-tuning stage for local information. So basically their experiment is trying to answer the question whether this kind of modification is effective, whether having these two separate modules can be better than before. So they measure the result using accuracy AUC because okay, so what they do is that they consider different budget levels. Say I can pick 5, 10, 15 edges, and for each budget row, I can compute the explanation accuracy for the graph I have the ground truth. Then they collect this value together to compute the AUC. It's not the regular ROC AUC we are looking at. And then they try to evaluate their model by considering removing different modules in their model. Basically, in the complete form is this refine at the very end, has both the class-wise attributor, meaning the different T's we used to get the mask for each class, and have the contrastive loss and have the fine-tune stage. And then for the other minus CT minus FT, they just drop these modules. So at the end, what they show is that both modules they proposed, the contrastive ones and the class-wise attributor for collecting global information, they all contributed to the final win of the refined model over these 4 baselines here. I think the relative improvement in terms of ACC AUC is not bad, right? These numbers look good, but I think you really need to rely on all of these modules to show you can achieve this kind of improvements. And another thing I hoped to see in their paper, but they didn't include, is that they didn't visualize any global patterns they might have discovered, because previously we only had the local expandability, right? They proposed to include the global expandability, but they didn't show anything like interesting learned by those class-wise attributors. Like I mentioned at the beginning, if we can learn a map, say from functional groups to the predict properties, we actually can drop the local explanation part just for each molecule, check that map. So that can be something good to have in my opinion, good to have for their experiment.
Can I ask a question?
Sure.
So it looks like they focus on individual edges, right?
Yes.
In the graph.
Yeah.
So what if I'm thinking of, like, in one of the examples, this molecule example you showed, right? So maybe the important feature would be have like a ring structure, like have 6 edges, right? Forming a ring that has a very unique chemical property, for example, right? Maybe that's the important thing. So how does this model recognize that? Because you can't miss one of them. You have to have 6 together. If you just have 5 of them, it doesn't count.
Yeah. So this is a great question. So in this case, there is no guarantee. So we can let's say we can think of it as like a connectedness requirement, right? So we want to have a full ring. We don't want any edges to be missed. But at least in this approach, there is no guarantee we can find that. The only way we hope to find a full ring, let's say just for this example, this is only a pentagon. But let's say we want to find this pentagon with 5 edges. What they can only hope for is that when I include all 5 edges, then this number becomes really big. But when I include only 4 of them, then this number becomes really small. So no explicit enforcement, just the hope the loss function can make that, can distinguish that and help find the whole ring. Yeah.
Yeah, but sometimes, so the ring structure, it doesn't matter whether it's happened here, or maybe there's another part of the graph have that ring structure, as long as there's a ring structure somewhere, right? And then maybe this molecule would have some property.
Right.
So in that case, it's not really specific to this particular set of edges, right? There could be another set of edges also possibly forming a ring. As long as there's a ring, then you would have that property.
Yeah, so in that case, it will be like, let's say I'm looking at my picture, maybe more helpful. Yeah, in that case, let's say in this case, we have more than 1 ring, right? So if we believe the final prediction is associated just with the ring structure rather than a specific ring, then we would hope the explanation method to find out all the ring. Given enough budget, we would hope it to find out all the rings, right? Yeah.
Yeah, but see if the user specify the budget, right? And even if it specify like budget, it would be like 6 edges, for example, right? Because I know 6 edges have a range. structure. But there's no guarantee that this algorithm would produce that exactly forming a ring, right? Could it be like 3 edges from somewhere, 3 edges from somewhere else, right?
Yeah, there is no that kind of guarantee. Yeah.
Okay.
I have seen that post-processing steps. Let's say I can probably generate like a multiple candidates as my explanation. So one of them is like a 6-edge ring. The other ones is like a 2 set of 2 3-edge pieces. Sometimes people do this post-checking to say, okay, those 2 3 pieces are not connected. Maybe I don't want to consider them. So things like this. But for everything we talk about so far, there is no guarantee to generate a connected ring.
Okay.
Yeah, I definitely feel like this is like a one problem for this research direction to go on. It's like we probably want to have more restrictions or more inductive bias introduced into this framework. For example, if we know in advance that connectedness is really important, then utilizing this kind of knowledge can be very helpful for explaining your particular graph, right? In this example I'm showing here, because we think the ground truth is just this NO2, not like a complicated ring, maybe connectedness is not that important. As long as I have both edges, it should be good enough. But if I have more domain knowledge, my model should definitely consider that. Otherwise, the total number of subgraphs within this graph is definitely too many of them.
Right. So in other words, this model is really edge level, like explainability, right? Not subgraph level.
Yeah. So I have also seen, I think in my last presentation, like last year's presentation, when I first introduced this topic, that time I went over one paper from ICML. They call it graph level explanation. What they did was that, like very high level, what they did was that generate a lot of subgraphs and try to do Monte Carlo tree search among them. That method worked better than JN explainer. It's not compared to this refined method, but that method worked better than JN explainer. I think, I don't remember the exact numbers, but also like maybe like this kind of improvement over JN explainer. But the problem was that that method was much slower. You can imagine trying to do Monte Carlo tree search of many generated subgraphs. They have to have like a very small size limit of the subgraph they can generate. Otherwise, the method won't scale. So there's really a trade-off here. If you want to more accurate or explanation, or you want to have different properties like connectedness or etc., or you want to have larger budget, you need to consider the scalability issue. But otherwise, if you want to avoid that exponentially number of subgraphs, you just want to quickly do your mask learning or anything, the mask has to be over edges rather than subgraphs.
Okay.
Okay, yeah. Any other questions? Okay, yeah, thank you for these great questions. I think this really gives me a chance to connect all these papers in my mind, help all the audience here to better understand what are the challenges for this line of research and what people have tried before and what is still unsolved.
Before moving on, I have a question. I have leaving in the chat. So is there any other evaluation metric instead of just measuring the task performance with the masked input?
Sorry, in the chat, let's see. Evaluation metric. So yeah, I think evaluation for this direction is almost like a new problem. I personally have seen at least 5 papers proposing different evaluation metrics for explanation method, because it's hard. It's unlike other, say, classification. We usually don't have the ground truth label. So in this case, this is one way. If you have synthetic data or so, you can generate it. You can consider the accuracy and AUC. Other things, In terms of accuracy, people have also proposed what they call the fidelity value. The next paper, I will introduce it, meaning you generate the subgraph, the subgraph should give you high probability for the original class it is predicted. People also talk about other evaluation metrics like consistency, because some of the explanation method, if you run it 5 times, it will give you different explanations. So you would like these 5 explanations to be same or at least very, very similar to each other. People have also talked about the sparsity. So what they are saying is that don't give me if I don't have like a budget requirement, don't give me a huge subgraph as explanation. Give me something really sparse, right? So even though I tell you the budget is 10, you probably give me a subgraph with only 5 edges. So this have all been used to as evaluation metrics for different perspectives of the explanation method.
Yeah, another question is that after this masking, is their output a subgraph or like a continuous mask? For example, like if they have a mask over a particular edge, is it like it definitely be either 0 or 1, or it can be a continuous value?
Yeah, so this is a good question. It actually depends on what you want. So for most of the cases, people will turn that into a hard mask and select the subgraph. But if you want something like this, right? So this is in the tabular data, not the graph data. But they can read out the values for each attribute, saying that this is 0.4, this is 0.1. If you turn it into discrete, you're probably just saying select the edge and the blood pressure. But you can also keep the mask and read out the value to say how to further distinguish, okay, edge is more important than blood pressure. In the graph case, maybe just for example, maybe this NO2 is more important than this 2 NO2 because it's far from this O, say. It's not symmetric, this O plays some role. Yeah.
So for the paper you introduced, they use hard masking?
They use hard masking, and then they actually for this paper, they explicitly distinguish these two because the GATT in their case is soft masking, but in the fine-tune stage, they output this GEXP, which is hard masking.
Yeah, then one naive question is that if it is hard masking, then there should be the upper bound, right? If you enumerate all the possible solutions.
What do you mean by upper bound? Like budget? Like how many?
Given the budget, there should be the optimal solution. If you just want to, like,
I see. You are saying that if rho is 5, we should be able to enumerate all subgraphs less than 5 edges and have the best one, right?
Mm-hmm.
Yes. Yeah, there should be an optimal solution like that. Yeah.
Yeah, but they didn't compare with that.
Oh, they didn't. Yeah. I guess. Yeah, this is a good point. I guess that means for all kinds of explanation method, we can first run the GNN with like a reasonable budget, right? So for each graph, we can have a reasonable budget and check all cases. Then we store that as the best case. Then later on, whatever we output, we can compare to that best case. But I have never seen any paper done that, probably because when rho becomes a little bit large, say maybe 10, that's already too computational heavy. They can only maybe afford 5 or something. Yeah. Okay. Any other questions?
Hi, Shichang, one small question. So regarding the mask, is it always that in the graph domain, they were trying to convert it into discrete one instead of continuous one?
So yeah, so this depends. I think this is related to Sunil asked. It depends on what you want the final output to be. So usually you can, let's say if you only want the soft mask, you can stop at this at that point, right? It gives you more information about how important each edge is, 0.4 or 0.1. But usually because people try to do visualization, they want to have a graph like this with some edges kept and some edges dropped. So they will turn it into a hard one.
Then will there be some performance differences between using the continuous mask versus a discrete mask?
So for the performance difference, you mean if I use this subgraph, the continuous mask subgraph and the hard mask graph to do the prediction, which one will give you higher probability, right?
Yes.
I think in most cases, people just use just evaluate the hard mask because they assume that will be the final output. That's what they call the explanation. The soft one is like more of like an intermediate step because you can imagine so because the M comes from a soft max, right? So you will have some really small values like close to zero, but not strictly zero. If you don't drop them, technically you are keeping all edges. Technically, you are keeping the whole graph just with some edges with very, very small weight. In that case, it's hard to say you are doing an explanation, right? So because you didn't tell like the subgraph that is most important, you just reweight the edges. But I think because the objective, sorry, where is the, yeah, because this objective is optimized using the soft mask, I feel like this may be, the soft mask may give a slightly better results than the hard mask.
I see, thanks.
Okay, any other questions? Okay, then let's move on. Right. This second paper, this will appear in this year's Neurips, and it's just made public very recently. So again, like the other one, I want to first talk about some of my general comments about this paper. I think the approach they are taking is enlightening. I think this is, later you will see, they kind of reduced the problem into the continuous case. I mentioned the challenge is that because the graph structure is discrete and the gradient-based method cannot be fully leveraged, etc. Here, the partial of their module leverage the gradient-based method. I think that move was very smart. But also something questionable about this paper, in my opinion, is that they try to solve a task, like in their title, they mentioned task agnostic. They actually try to do multitask explanation. I personally have a little bit of concern about how useful that task can be. So seems like they made a smart move, but I don't see the real benefit brought by that smart move. But let's look into the detail about what this paper is doing. So basically, the question they ask is that, can we have a single explainer that works for multiple tasks, right? So in other words, the specific problem they are trying to solve is in terms of efficiency. They are saying that if I am in a multitask setting, in the general setup of GNN explainer or refine we just saw, it's like always one graph, one prediction, I explain it. One graph, one prediction, I explain it. That can be slow. But if I can have some general framework for this specific graph, you want to make 100 predictions about it, I can explain all of them very fastly. Then that can be beneficial. This is their motivation. So to do that, they actually separated the whole explanation step into two stages. The first stage, they call it an embedding explainer. The second stage, they call it a downstream explainer. The presentation of this paper is actually very good and very clear to, at least in my opinion. So everything can be illustrated using this framework graph, and we can look at each of them one by one. So first of all, is a problem setup. What they assume is that, well, we have this input graph, and then I have some multitask module to classify this. Let's just think of it as graph classification, to classify it for different tasks. And then what I can do is that I can just get the prediction from this module and then use multiple explainers to explain what's happening for for each task, right? And then this number, this task-specific explainer can grow large. So that's the problem we try to solve. But if we further look into what's happening in this multitask module, for most use cases of GNN, this is what's happening within that multitask model. So what's happening here is that for the input graph, I just embedded get the node level representations, or I have a final readout function to get the graph level representations. But in any way, I will just turn this graph into vectors, right? And then up to this point, if I'm doing multitask prediction, I probably have a lot of like a downstream prediction head. Like for each of them, I think of them as like an MLP, which just turns this embedding vector into, say, the binary prediction, the probability value I care about. So if this is what's really happening within the multitask model, then what we can do is something like this. So basically, they want all these different prediction heads to have one shared embedding explainer, and each of them only have their own downstream explainer, meaning from the graph up to this embedding point, everything can be explained using one single explainer. And then this single explainer mathematically is this TE, which takes this embedding in D dimension and the input graph G, and gives you another subgraph, or in this case, G can be think of as like the space of graph or the random variable of graph. But basically, your output is another graph, subgraph as your explanation. And then once you have that, no matter how many prediction heads you have, for each of them, you can just have like one downstream explainer. The downstream explainer will take this D. This D is your final like classification result, plus this embedding vector, which is this blue one, and tells you they call it like a conditional vector, and then this conditional vector will be used into to plug into this embedding expander. So in this case, they actually separate things into two. So for the downstream explainer, because all three things here are continuous, so they can just do it using very simple gradient-based method that people started to study in 2014. That part is pretty mature. And just for this part, to generate the subgraphs is hard, but because they are sharing it among many tasks, so even though it's hard, it's slow, it should be affordable. That's the general idea of this paper. Then another thing about this paper is the training of this embedding explainer, so which is showing in this graph here. The good thing is that the training of the embedding explainer is actually independent of the downstream tasks. This is also related to, maybe this is better to call it a pre-train and fine-tune stage. I don't know, but this has this related idea as the previous paper, where they first do this embedding explainer training. In this step, they don't need any labels. They don't even need any downstream task, because all you want is a model from graph to an embedding vector, and then you try to explain what's happening. Then what you can do is that you can generate many random embedding vectors, right? Because you don't have any task. You just try to figure out relationship between input graph and some RD vector. Then you can randomly generate a bunch of them, figure out the relationship. Later on, no matter what kind of vector the downstream task is asking, you have the probability of generating them in your random samples. Then you can use your trained embedding explainer for that downstream explainer. So in this case, if we write down the formulas, it will be this. You want to train this TE, and then you just draw random, what they call the conditional vector, the random conditional vectors from a Laplace distribution. So in the graph, it's like this. You have this you have this input graph. You have this input model. It will output it will embed your graph to get this embedding vector. And then what you can also do is like you can use your embedding explainer to generate another embedding vector. And then for these two vectors, they will both be masked by this randomly generated condition vector. This randomly generated condition vector is saying, the idea is saying that, okay, which dimension of this vector is important? Then you match the masked of these two also by the same mutual information loss we have seen before, right? Okay, any questions about what's happening here? Okay, great. So, and then they specifically mentioned what's happening within the embedding explainer, like the architecture they used is also very similar to the refine case. Like remember in the refine case, we connected the two node embeddings and plug them into an MLP, right? Pretty much like doing a link prediction. In this case, it's the same thing. The only difference is that they are masking it using the condition vector, because the condition vector represents which dimension of this vector is the one you care about. Also, for node level tasks, they concatenate the third vector to it. This is like saying, I try to predict the edge between node I and node J, but this prediction is meant for classification of the node target, right? So let me repeat again, there are 3 nodes involved in this case. I try to predict the link between node I and node J, so I need both of their representations. But this prediction is meant to later on explain the classification of node target. So I'm going to take all 3 of them, concatenate them together, mask them by the conditional vector, and using this plug it into this MLP. So in this case, the WIG we generate here is pretty much the mask we saw in the GNN explainer and the refine case. So that gives us the embedding explainer and the downstream explainer, right, which is this one. With all 3 things as continuous, is pretty straightforward. They didn't propose any new thing. They just used a standard gradient-based approach. Meaning in this case, if you have this prediction, dz, z is your embedding, right? Based on your embedding, you make classification into in total of all C classes. Then what you can do is that you just take this result, find out which is the class you pick, right? Maximize the maximum small c of C, and then you take the gradient with respect to your input Z. So this will give you that for this input embedding, which dimension was most important for classifying Z as the class small c. So once you have that, they normalize it and plug it into the value to get the conditional vector. So through this conditional vector, the explainer, the embedding explainer and the downstream explainer are glued together. This is the bridge here. Okay, then in this case, here they are evaluating their results using the fidelity metric. Basically, they checked the molecule net dataset with you are probably familiar with this. These are all molecule graphs, and they have this protein graph as well. So in this case, this is multitask because there are 121 tasks involved. They argue that if using other explainers, doing this 121 times will be pretty slow, but in their case, it will be pretty fast because the downstream classifier is just one round of gradient. Is basically instant. So they only need to train one embedding explainer. And then this is the metric I mentioned about fidelity and sparsity. Zhenyu also asked about it. I think, yeah, we are running out of time. I'm just telling you, you can check the formula later maybe, but I'm just telling you for fidelity, it's the higher the better. For sparsity, it's also the higher the better, meaning you want a sparse explanation with high fidelity. And what they do is that they plot the fidelity against the sparsity plots for all different methods. And then they are showing that their method, TAG explainer, is the best among all of this. Oh, they have another, I think, interesting comparison is saying that because they only trained one single embedding expander with different downstream expanders, they can test that how good that can generalize to different downstream expanders. But they also did something, I guess, for the other specific expanders, say trained on this BACE dataset to test whether that can generate to expand another task. I guess this is pretty much expected, right? If you use something trained on BACE and generate it on HIV, the performance is almost close to zero. So in this case, they are saying that, well, others cannot, you cannot naively take others and generalize them, but you can take their method and generalize. The final thing is the efficiency evaluation, because this is what they claim the major contribution of the paper. So they are saying that using their method, right, the last one here, they can achieve like a speed up compared to the JN explainer and another baseline PJ explainer they mentioned. They are saying in this case, if there are total 121 tasks, they can achieve regarding these two baselines 33 times faster or 12 times faster for explaining all 121 tasks. But my question for this paper, this specific experiment, and also this paper in general, is that, like, how critical can this kind of multitask setting be? I actually discussed it with some other researchers doing gene explanation. I think maybe one setting this could be useful is that if you have say 100 classification task, you probably reformulate it as like 100 binary classification tasks. People told me that sometimes the model can be more accurate if you do the binary classification 100 times. In that case, if you want to explain that model, then you probably want to consider the setting here, because you don't want to repeat things 100 times. But in other cases, it's just I personally find explaining multitask classification is not it's not super common for the data sets I have seen. Yeah, maybe if any of you have ideas, you can also let me know. Okay, this clears all I want to talk about. Any questions for any of the paper or general explanation in general?
Okay, thank you, Shichang. So what I want to mention is, like, Shichang, you also have a couple of papers, including a paper that in summation related to the topic. So I really strongly recommend that for the reading group, we don't have to just talk about other people's work, okay? You can also kind of introduce our own work and try to kind of encourage or promote some discussion among ourselves. And we try to inspire each other and establish like collaborations.
Okay, yeah, that will be even better. Yeah. Okay, if no other questions, maybe we can stop here. Yeah, thank you everyone for the questions. I think we had really nice discussion today.
Yeah. Okay, thank you.